We're continuing to work with matrices, but we are looking at them in a slightly different way. In this section, we're not really looking at how we use them to solve systems of equations. We're going to look at how we use them to do other things. And I hope in here you'll see some applications that kind of give you an idea of what this might be used for. We are going to add and subtract matrices. We are going to multiply a matrix by a scalar. We'll define what scalar is. And then we're going to multiply matrices. And last, we need to talk about finding a matrix equation. That's going to take us a couple of videos. Matrix multiplication takes a little bit to unpack that. So in this first video, we'll probably just get to adding and subtracting matrices and then scalar multiplication, and possibly a little bit to start multiplying matrices. This data was given in a table earlier in this unit. And so it's kind of like this matrix, right? You could put that in a matrix with this information. Scenario number 1 says, what if you wanted to add shrimp and cauliflower and mozzarella cheese to your recipe and wanted to see the same data for the protein, the veggies, and the cheeses? In that case, if you had a similar matrix with the same information where the first row was shrimp, the second row was cauliflower, and the third row was the mozzarella cheese, if you were somehow able to add those first row numbers and the second row numbers and the third row numbers, it would give you the total information for the proteins, the chicken and the shrimp together, the vegetables, the broccoli and the cauliflower together, and then the cheeses together. So we're going to see something like that. Scenario 2, what if you just wanted to double the whole table because you actually have 2 ounces of chicken, 2 cups of broccoli, and 2 ounces of cheese? Instead, you want to just double all these numbers. Well, you can do that with a matrix operation. Last, what if you wanted to see the numbers that you would get for these if you had 6 ounces of chicken, 2 cups of broccoli, and 3 ounces of cheese? Similarly to that application problem we did that said you want these total values for calories, protein, and fat. How many ounces and cups of each do you need? Well, now we're saying, okay, I have this much. How many total calories would I have? How much protein would I have? How much total fat would I have? And so on. So a couple of scenarios here that I can foresee being a thing, right? So we're going to look at those. These can all be done with matrix operations. One little note here. A sub ij, remember how we did rows by columns on the size? The I refers to the row and the J refers to the column that you're in. So A22 means the second row, second column. A31 means the third row, first column. That's that 115. Just in case we need those. Okay. Addition and subtraction of matrices can only be done if the matrices are the same size because you add or subtract the elements in the corresponding positions. So A11, B11, we add those together to give us 5. 6 plus 4 gives us 10, and it goes in that top left. 2 plus -6 is -4. 1 plus 1 is 2. So you add these numbers that are in the corresponding positions. This guy, one thing we should write here, this is 3 by 2, 3 rows, 2 columns. This is also 3 by 2. They're the same size, so you can add them. This one is 2 by 2, and this is 2 rows by 3 columns. Not the same size, so this is not possible. You cannot add matrices that are not the same size. Which scenario above uses this? That would be that scenario 1, where you wanted to add shrimp, calories, fat, and protein to the chicken. You want to add cauliflower, fat, calories, and protein to the broccoli, and so on. You would just add, you would set those two matrices side by side and add those corresponding things. I just did a third example here with subtraction because it's really easy to lose track of your negative here, so be careful. -2 minus -2 is going to be 0. 4 minus 1 is 3. 6 minus 3 is 3. -8 minus 4 would be -12. So that's that matrix with the subtraction in there. The next type of operation we're going to look at would be scalar multiplication. A scalar is any real number. The reason that we give it a different name, especially when we're talking about matrices, is because it's really easy to confuse something like the number 5 and the matrix 5. This is a scalar. This is a matrix. So we want to distinguish those. When you have scalar multiplication, you multiply every entry of the matrix by that scalar. In this case, -4b, we multiply, this would be -4 times 2, -1, 0, -3, 1, 5. And that gives us -8, 4, 0, 12, -4, -20. That's -4b. Down here we'll do the same thing, but we have some subtraction in addition to two scalar multiplications. 2 times a is going to give me 2, 0, 18. -1, -8, 12. And to that, oopsie, I want to subtract. Let's do 7 times b is 14, -7, 0, -21, 7, and 35. I really wanted to multiply by -7, which you can do. You can add this and multiply by -7, but that's why I was hesitating a little bit there. It didn't feel natural to me. Now let's subtract to give us -12, +7, 18, 20, -15, -23. Which scenario above uses the idea of scalar multiplication, not this addition business, but the idea of scalar multiplication would be scenario 2, where we just wanted to double everything in the matrix. Okay, matrix multiplication. We'll probably just introduce this a little bit. We'll see what we have time for here. An m by n matrix A is multiplied by an n by p matrix B to give an m by p matrix AB. So first, what we're talking about here is not how we multiply them, but if we can multiply them. Just like you can only add or subtract matrices that are the same size, here to multiply matrices, we don't need them to be the same size. We don't even want them to necessarily be the same size. What we need is the number of columns here to match the number of rows in the second matrix. The result then is the number of rows by the number of columns in these outside dimensions. Let's look at this example. If A is 2 by 3 and B is 3 by 4, then AB is, well, these match, so they are, you can multiply them, and your result is 2 by 4. For this one, if we want AB, 4 by 2, 2 by 5, the 2's match, our result is 4 by 5. Here, A and B are both 3 by 2. These do not match. That means AB does not exist. I think an important thing to talk about here is the fact that in this scenario, AB exists, but BA in part B here does not exist. You would be trying to multiply a 2 by 5, would be the first one, by a 4 by 2. Those don't match. So you cannot multiply BA. That's an important distinction about matrix multiplication. If AB exists and is 4 by 5, but BA does not exist, clearly that tells us that AB is not equal to BA with matrix multiplication. It's not like numbers. When you multiply two numbers, you can switch the order. We call that commutative, and you still get the same result. Matrix multiplication is not commutative. Even if it does work, that you could have, so say for example, they're both 2 by 2. You can multiply both of those, but the result will not be the same, even though they're the same size. Let's talk a little bit about how we multiply matrices. We are first going to talk about multiplying a row matrix by a column matrix. And then we'll expand that. What if they're not row matrices or column matrices? If we want to multiply this 1 by n, it has n items here, and the column is n by 1, has n rows, 1 column. We want to multiply those. Our result should be 1 by 1, right? Because the n's they match up and they disappear, leaving 1 by 1. There really should be a bracket on that because it is a matrix that you get, a 1 by 1 matrix. Here's how we multiply a row matrix by a column matrix. We multiply the first item here, A11, by B11. Multiply those two. Then we multiply A12 by B21. That goes here. That product goes there. And so on. You keep going all the way down to the last item multiplied by the last number there. That's this result. And you add all of these up. This is why we get a 1 by 1, because we're multiplying a bunch of numbers and then adding them. So it's all going to simplify down to a single number. Let me show you what I mean. We have a row matrix by a column matrix. This is 1 row by 3 columns. This is 3 rows by 1 column. We will get a 1 by 1 when we multiply this. Here's how we do it. We multiply the 3 in this first position by the 1 in the first position in the second matrix, plus 1 times 5, second position, plus 4 times 9. That is 3 plus 5 is 8. Plus 36 is 44. That's a 1 by 1 matrix that we get from that. When we want to multiply a non-row matrix by non-column matrices, we do that same action where we multiply a row by a column, but the result goes in that position. So to find the row 1 column entry of the product, we multiply the first row of A by the first column of B. row 1, column 2 entry of the product, we do the first row by the second column, and so on. I like to do this with circles, kind of. So this, first of all, we have to make sure we can multiply it. 1 row by 2 columns. This is 2 rows by 3 columns. That tells me that my result, AB, will be 1 by 3. Okay. We multiply the first row by the first column. We do that by multiplying 1 by -2 plus 3 times 8. Whatever that number is, it goes in the first row, first column position. Then we multiply for the second position, second answer, second number we get there. We're going to multiply, oopsie, this row by this column. 1 times 0 plus 3 times -4. Then we multiply the first row by the third column, and we put it in the first row, third column position. 1 times 4 plus 3 times 9. Now let's simplify all of these up. -2 plus 24 is 22. 0, 1 times 0 is 0, plus -12 is -12. And then the red one is 4 plus 27 is 31. And that is our 1 by 3 matrix that is the product of these two matrices. Let's do another example. Always rows of the first matrix by columns of the second matrix. We are going to multiply this row by this column. Well, first let's make sure we actually can multiply these. This one is 2 by 3, 2 rows, 3 columns. This one is 3 by 2. So the result will be 2 by 2. AB will be 2 by 2. So let's do this. We multiply, so we know we're going to be 2 by 2. I'm going to leave us plenty of space here. We're going to have an entry here, 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 and here. We have 2 by 2. Let's figure out what those entries are. 3 times -1 plus -4 times 3 plus 2 times 5 is multiplying that first row by the first column. Now let's go to multiplying the first row by the second column. That means we're going to put it in this spot because that is the first row, second column position in the result, right? If you're multiplying the first row by the second column, you're going to put it over here in the first row, second column. Erase that, I might need more space. So we do 3 times 2, first row, first position by the first position, plus -4 times 4, plus 2 times 8. Remember how I said that I use my fingers a lot with the matrices? That is exactly what I do here. I kind of hop down. I point to the 3 and the 2. Then I hop over to the -4 and down to the 4. Then I hop over to the 2 and the 8. And I multiply those numbers and add between them. Now let's move on to the bottom row, first column. Second row, first column. That tells me I'm going to use my second row here and my first column here. So I do -2 times -1 plus 1 times 3 plus 6 times 5. Last comes from multiplying the second row in the first matrix by the second column in the second matrix. That gives us our second row, second column position. -2 times 2 plus 1 times 4 plus 6 times 8. And then let's go ahead and actually calculate what these are. -3 minus 12 is -15, plus 10 will give me -5. The blue number here will be 6, minus 16 is -10. Oh wait, plus 6, minus 16 plus 16, so that's just going to give me 6. 2 plus 3 is 5, plus 30 will give me 35. And last one, -4 plus 4 is 0, plus 48. And that is our answer to how we multiply these two matrices, that 2 by 2 result. Okay, we're going to look at some applications of matrix multiplication. So let's take some time for that. So I don't want this video to get too long. So I'm going to stop it here. And we'll come back and look at another matrix, another video with matrix operations.